This short presentation introduces thinking about energy in the context of capacitors. So what we're going to do, or what I'm going to do for you, is I'm going to show you how to calculate the work required to separate charge on a capacitor. And you might use language like this. What's the work required to, and I'm putting it in quotes, charge up a capacitor? But if you remember from my previous presentations, we're considering cases where actually the capacitor does not have a net charge other than zero. That is, whatever we move from one of the plates of the capacitor, we put it on the other plate. So we never ever take the charge away, or we never add charge to a capacitor. So we're not literally charging up a capacitor. We're separating charge on the capacitor. So here are two relationships. They're the same relationship, actually. It's just one's an algebra step away from the other. But the definition of capacitance is what is the ratio of, if you were to cause charge separation Q, what's the potential difference across the capacitor? And it turns out that this is something of a fundamental quantity that actually only really depends on the geometries and separations of the two pieces of metal involved. Okay, but I'm going to end up using the definition of capacitance, this second one here, right? So I'm going to imagine doing this exploration based on the parallel plate capacitor. And because it's really just the easiest to study or to imagine, and the circuit symbol diagram, right, that kind of looks like, it looks like a parallel plate capacitor. It just looks like what you're used to. But the truth is the results I'm about to get, they apply, they're going to be the correct result for all possible geometries of capacitor. All right, so here we do, right, we want to study what is the work required to separate charge on a capacitor. So we're going to imagine thinking about this in terms of a process. And the process starts right here. And we're going to say that there is no energy in the capacitor if there is no charge separation. And what we're going to do is imagine some sort of external person. You could imagine a little person, I'll just draw them real quick, being responsible for causing changes on our capacitor. So this little person is going to be an external influence. So they can come into the capacitor system and move stuff around, right? Expend their own energy in order to add energy to the capacitor system. So I'm thinking in terms of the conservation of energy. So this little external person can do external work, and they can cause, during the process, a step to show up where actually this person has accomplished separating some of the charge. So if they manage to separate the charge little q, right, by doing some work, then at this point, there is going to be a potential difference across this capacitor, which is just simply equal to, right? We'll just use this. It's the amount of charge separated divided by the capacitance of our capacitor. So I'm imagining this capacitor, which I've drawn at 3 different times, right? This is the starting point, some midway point, and then the final step of the process, or the final situation. But anyways, at this intermediate situation, I have a potential difference. At the starting situation, though, not only is there no energy stored there yet, there is also no potential difference because I don't have any charge, right? If you just want to know why is the potential difference equal to 0, you just go all the way up to the formula. It's because the charge that's been separated so far is 0. right? So there's no potential difference. Also, we say that this situation for the capacitor with no charge separation, we call it the situation of no stored energies. Okay, so anyways, at some intermediate step, right, this person has definitely done some work to arrive at this situation. And they're about to take the charge. I'm going to say it's a small amount of charge, and they're going to move it from the negative place. You imagine dq is a positive charge. So this person is going to move it away from the negative place towards the positive place. That takes a positive amount of external work because you're fighting the tendency of this little positive charge just to go right back to where it started from. So you fight with it, you add energy into the system by making the charge separation even worse or increasing the potential difference. So the amount of work required to move this little charge from the negative plate to the positive plate is equal to the amount of work required to move it up this potential difference, right? Remember that that's how we associate potential difference to some physical sort of exertion. The idea is to move a charge across a potential difference requires a work. And because we're moving an infinitesimal amount of charge, like a calculus small amount of charge, the amount of work to do that is also calculus small. So this delta V, though, is right here. We have to fight this intermediate potential difference. It's the potential difference that we've gotten to by the time of the middle step, where the middle step is characterized by the fact that we haven't moved all of the charge yet. We haven't separated the charge fully. We're just somewhere midway along. So this is just dq q over c, right? Q over c. So in order to calculate the work required, we're going to add up all of the small amounts of work to finish the entire job, right? So the result of the process is to change the charge separation from 0 into a final charge separation. Let me change colors now. Of this. And in order to accomplish this process, that external person needs to do the whole job of separating the charge starting from no separation at all to some final separation, capital Q, where at each step of the process, they have to do a small amount of work, which is equal to dq q over c. So you can see that the integration variable shows up on the top here. And this is the sort of the integration step, right? And if you just do your calculus, this is, right, so the integral of q dq over a capacitance, which is independent of the charge. So this capacitance actually can live outside. So I'm going to do that as an explicit step. It's independent of the charge. And what you have is q dq, which looks like x dx, right? And the result of doing this integral is q squared over twice c. Can you finish those steps? Right? I skipped 2 steps essentially. So I think that you should make sure you know how to finish that. Right? So there's 2 steps in there. But anyways, if you started with 0 and we just said that there is some external source of energy and they do this much energy, right? Then that means that this must have changed the energy of the capacitor system. And we're going to say that the only energy that this work was able to change was a potential energy of that capacitor system. And we say that we start with no energy. So after causing a change with this work, the energy of the capacitor after being charged to this state right here is equal to Q squared over 2C. All right, so yeah, so this is a basic result. And again, all the results apply to all possible geometries of capacitor. So even if this C right here was for a cylindrical capacitor, which I introduced in a previous video, or the spherical capacitor, right? It doesn't matter. If you know the capacitance, which is going to come in some number of farads, then if you caused a charge separation of capital Q across whatever capacitor you had, then the energy that you're going to store up is this. All right, so we can actually say something really interesting. So here is something, and I'm going to say that it's more than interesting. I'm going to say it's something fundamental. So the fundamental thing is this, let's say you have the parallel plate capacitor. So here is one of the plates, and here is the other plate. So they are, or I don't know if you remember, well, I hope you remember, that we got this capacitance, which was let's see, which way was it? It was, I always have to remember. So right now I'm looking at my book. I apologize. I don't have a good memory for details while I'm lecturing. So I always have to look back. So the parallel plate capacitor, is A over epsilon naught D, I think. No, it's epsilon naught A over D. So it's A over D times epsilon naught. Yeah, so the epsilon naught is on top. Okay, so this result comes from an approximation, right? We're approximating that the area and the separation distance is really, really small compared not to the area, but in a sense to the square root of the area, or the edge, right? The edge length of the sides of the rectangles. So in this approximation, the reason we made that approximation is because in this approximation, the electric field is uniform, right? So the electric field is uniform everywhere in between these plates. So let's imagine we put the positive charge on the left plate and the negative charge on the right-hand plate. Then what this is saying is the electric field that's in here is uniform, only points from the left side to the right side. So everywhere it's the same value. All the electric field lines are nice and straight. And what's more than that is actually in this parallel plate capacitor, we can say that the electric field outside is just zero. That is, the electric field only has value that's not zero inside of this capacitor. And the inside of the capacitor is a certain volume of space. Remember that this, from the side, it kind of looks like the following thing. So it sort of looks like a book. right? So in this volume in between, right, you have area A and distance of separation D. So the volume of space, I'll just say it, volume equals A times D. So the volume of the space in between the plates is A times D. And here is the fundamental statement. The energy is localized to this volume in the form, of a uniform electric field. What we'll say is there is an energy density, it's a lowercase u, which is the energy stored up in the capacitor because of the charge separation right here, divided by the volume, A times D. So let me caution you, we are only talking about the parallel plate capacitor right now. But again, even though I'm going to derive a result from the parallel plate capacitor, it's still going to apply to all possible geometries of capacitor, regardless of what kind of capacitor you're talking about. But what I want to do is say that, this is our potential energy, but it's a potential energy per volume. This is an energy per volume, which is called energy density. So this thing right here is energy density. So the units for this, for example, would be joules per centimeter cubed, or joules per liter, joules per meter cubed, right? Some energy unit divided by some volume unit. That's what this is, right? Because it's energy divided by area times distance, which is volume. Okay, cool. So let's move on. I want to say something extremely fundamental. So let's see. I'm looking at my notes right now. Okay. So capital U, let's go back and look at something. Let's see. So capital U is this Q squared over 2C. Let's put that in there. So this is capital U, right? The energy. So Q squared over 2C. I'm going to kind of like fumble around because so let's see what I get. So really quick, C is Q over delta V. Instead of writing this in terms of Q squared, I'm going to write it in terms of, should I do this? No, I'm not going to do that. Let's just see where I get to if I just continue working. So I've got this statement, and so now I can write that the energy density, this lowercase u, is Q squared over A times D times 2C, right? Here's the 2C, and I need to divide by A times D, so that's all that stuff. All right, so let's go and do the following thing. So U, couple of things. What if I did this? So here's the thing, like me as a teacher, I have a certain goal in mind because I've already seen the result. So right now I'm essentially just trying to force the result to show up. So I'm going to try to force the result to show up. So an interesting thing, right? I want to write this thing in terms of our electric field's magnitude. So the electric field inside of a parallel plate capacitor, when we have this approximation that the electric field is uniform, remember that the electric field is going to have a magnitude that's sigma over epsilon naught. There's no factor of 2 because actually each plate contributes sigma over twice epsilon naught electric field, and they combine, right, half and half make a whole, so sigma over epsilon naught. So I want this to show up in my expression for u, so I'm going to force it to show up. One of the ways that I can see it get forced is I know that sigma is simply the charge on one of the plates divided by the area. So I'm going to take one of the q's, divide, and it's already divided by the area, so I've still got q over d, right, times 2c on the bottom. But this q over a is sigma. Yeah, let's see where I get if I do this. So I got sigma. I want divided by epsilon naught, so let me divide by epsilon naught and multiply by epsilon naught. So I've got epsilon naught on top now. I've got q over d times 2c. There's definitely a better way to do this, but I'm just messing around, and maybe you'll get something from me messing around for a second. So, so I really want to have this epsilon naught, so I'm going to force it to show up, but I can't ruin the equal sign. So I need to also, if I'm going to divide by it on purpose, I need to multiply by it, so I'm only ever adding a factor of 1. So I've got q over a. I put in an epsilon naught, so I had to put in another, so I didn't ruin the equal sign. And I've got q over 2 times c times d. All right. So at this point, oh, you know what I'm going to do? Should I do this? Yeah, I'm going to do it. I'm going to multiply by a over a. So yeah, what the hell? So I got sigma over epsilon naught, and then I've got q over a again. Oh man, I wish I didn't do this. But I did it, and you know, like the one takeaway from this is to remember that you're not doing anything wrong unless you do your math wrong. So I'm just going to continue to follow my nose, as clumsy as it's turning out. So I'm actually going to do, yeah, so we did this step. We've got sigma over epsilon naught. I had to add the epsilon naught. And then I'm doing this a over a, and then I'm going to do it again, epsilon naught over epsilon naught, right? This is just a factor of 1 that's interesting. So I have all kinds of epsilon naughts all over the place. I've got epsilon naught squared, but I'm going to take this q right here, this a, and this epsilon naught, and I'm going to make another sigma over epsilon naught factor, right? So at this point, I've written this one. So I'm left over with epsilon naught squared on the top because I had 2 factors of epsilon naught that I had to put in. That q over a, so I've got epsilon naught squared so I have handled this one. I have handled this q, this A, right? Because, and this epsilon naught, because that's here. And then I've got this epsilon naught and this epsilon naught, they're here. So the things that I haven't included is this A, which is on top, this D, and this twice C. Right? Yeah. So just algebraically, you can go and make sure that I did everything right, but I think I did everything right. So I'm inspired as the teacher. I know where I want to go because I've seen where you can get. I just need to reproduce the path. You as the student might be like, what the hell's going on? Which is not a bad position to be in. But this right here is just the electric field. So I've got two of them, which means I've got the electric field strength squared, right? This is the value of the electric field in the parallel plate capacitor. And then I've got this epsilon naught, but check this out. So do you remember that the capacitance of our parallel plate capacitor is epsilon naught A over D, right? So that's what the capacitance of the parallel plate capacitor is. So I'm going to put that in, but I've got this epsilon naught squared. I've got A over D, and then I've got a factor of 2, and then I've got C on the bottom, right? C on the bottom is the same thing as putting D on the top and epsilon naught A on the bottom, right? That's the C. So I've got the expression looks like this now, and remember we're calculating this energy density. So the energy density now is the magnitude of the electric field squared. And now I got a lot of cancellations to do. So let me switch colors again. There's an epsilon naught on the bottom, but I've got two factors on the top. So one of them on the top goes away, and all of it on the bottom goes away. I've got a factor of D, gone. I've got a factor of A, gone. And the only thing left is epsilon naught over 2. Like this. So we have this result that the energy density is equal to the electric field magnitude squared epsilon naught over 2. And this is really, really important. We're going to claim that there is energy associated with electric field. And this is how you understand the energy. So the point is if you had an electric field, right? So here's some electric field line diagram. This electric field is a function of spatial coordinate, right? So if I wanted to say like here is a position whose coordinate is x, y, z, we would say, well, there's electric field right there at that location. And the electric field right there at that location means that in that little volume of space, that's a dx, a dy, and a dz, there is energy there because there's electric field there. And the idea is the amount of energy that sits in this super small cube of spatial volume, the amount of energy that sits there is equal to the energy density times the volume. Because remember, in terms of like physical dimensions, little u is energy per volume. So if I multiply by volume, I get a small amount of energy, right? A calculus amount of energy. So there is a small amount of electric potential energy that sits in that volume of space simply because this electric field sits in that small volume of space. And that's a fundamental sort of claim on why an electrical system would have energy. The electrical system, in this sort of understanding, the electrical system does not have energy because electric charges are separated. The fundamental reasoning is that your system has electric field. That's why it has energy. Yeah. So this result that we got, this thing right here, is another one of these results that I'm telling you is irrespective of what kind of capacitor you're talking about. So actually, this result is not only for capacitors. It's just strictly a result about electric field and energy.